Last week we defined the centripetal with a P force as that force that acts on an object moving in a circle that directs it toward the center of the circle. When I swung those keys around my hand last week, it was my hand that supplied the force that kept it going in a circle. And that hand was in the middle of the circle, which meant the centripetal force had to point toward the center of the circle. Now, the end of last week, we defined a new force that we called the centrifugal force, centrifugal with an F. We said that was the force, and we say that in quotation marks, that's the force that acts outward, away from the center of the circle, toward the outside of the circle. When you go around a turn, you feel as if you're being pushed out toward the outside of the circle. But what did we say about that on Friday? What did we say about that centrifugal force on Friday? It's not real. You think it's there, but it's not there. We feel it. We physically feel it, but yet it doesn't exist. How do we physically feel something or physically observe something when it doesn't really exist? Well, it's all your frame of reference. If you have an object going around in a circle like this, let's say it's going counterclockwise. This is the center of the circle. Let's make this a merry-go-round. Okay? When I was a kid, at my elementary school, we had this great merry-go-round, and everybody every day wanted to go to the merry-go-round. But there was 4 bars on that merry-go-round, and on one of those bars was this scratch, like this deep scratch in one of the bars. And for whatever reason, nobody wanted to go on that bar. Nobody wanted that bar. Okay? There was no real good reason for that. It wasn't like it was sharp. It didn't hurt. It just, everybody avoided that bar. Okay, let's say that scratch is represented by this green dot. Okay, that scratch is represented by this green dot. Let's say that I'm the last kid out for recess in the morning, and I have to go on that bar. I'm at the scratch bar, we'll call it, okay? I'm right here. Okay, I'm close to the center of the circle, but I'm on this scratch bar. Make sense? Okay, I'm in line with the center of the circle, in between the center of the circle and the scratch bar. Make sense? Okay, a fraction of a second later, like let's even say half a second later, this scratch bar is right here. Agree? Because it's rotating counterclockwise. So the scratch in this bar is not in the same place anymore because of its rotation. Well, if that's the case, then I'm not there either. Okay, I'm not there either. But what happens? I'm going off. I'm not going out to the center of the circle. What happens is I'm going in a straight line. What happens a half a second later? The scratch bar is right here. What happens to me? Well, I'm going in a straight line. Half a second later, the scratch bar is right here. What happens to me? I'm going in a straight line. Do you see my path? Okay, my actual path is a straight line here. What does it look like my path is from my perspective? Okay, if I close this up, put a curtain around this merry-go-round, and I can't see the outside, my perception is that I started close to the center of the circle on that bar. Now I'm a little bit further out on that bar. Now I'm a little bit further out on that bar. And now I'm at the end of that bar. So what did it look like to me? It looked like I was pushed out to the outside of the circle on that bar. But really, you can see, as observing it from the outside, I really just went in a straight line. So what is this centrifugal force that we talked about on Friday? It's really just, what's the word? What's the I word that it really is? It's really just inertia. It's really just me, or whoever it is, or whatever it is, going in a straight line. It just seems as if that thing is being pushed to the outside. Now, let's say that I'm on the outside of this now. Let's change it from a merry-go-round to that ride at Callaway Park that spins you around and pins you against the wall. Now I'm not going out, because now I'm already out at the edge, right, Tiana? I'm already out at the edge. I physically feel myself being pushed against the wall. But I'm not being pushed against the wall. really, it's just my inertia that wants to take me in a straight line still, and the wall pushing me in. Remember we said that whenever we have a force or an acceleration in one direction, we have a pseudo force or a fake force in the opposite direction. When I'm sitting at the stop sign and I floor it, I put my foot on the gas pedal hard and I accelerate forward. I accelerate forward, but it feels like I'm being pushed back into my seat. When I'm accelerating toward the center of the circle here, I feel like I'm being pushed outward away from the center of the circle. So, centrifugal force is inertia that takes you to the outside, and that is sometimes combined with the centripetal force, centripetal with a P, that pushes you to the center of the circle. Does that make sense? Sometimes we hear that term centrifugal force. I've heard it in tire advertisements before. Okay, this tire is built so well it withstands high centrifugal forces. Well, it does have to be able, it does have to be strong, and it does have to be able to withstand forces, but it's not centrifugal force that it has to withstand at all. They're just using that as a marketing thing because they think people expect to hear that word. Okay, really, it's the centripetal force that it has to be strong enough to apply, not the centrifugal force that it has to withstand. So when you hear that from now on, think it doesn't exist. Okay, if you're with somebody, tell them, hey, you know, that doesn't really exist. Really, it's just your inertia and your centripetal force. Make sense? All right, today we're going to move on and deal with some more circular motion, but deal with kind of a neat situation of circular motion this time, and that's a vertical circle. This is going to rear its head next Tuesday on your amusement park field trip. A few times, actually, a couple times. You guys know that when you ride a roller coaster, you're going to go, in fact, the Mindbender at West Ed has 3 upside down loops, 3 vertical loops. So you're going to go upside down 3 times on that roller coaster. We need to be able to analyze the circular motion nature of you going upside down in that loop. So let's draw it out here. First, understand that on a roller coaster, it's not actually quite a circular path. It's more a teardrop shape. But we're going to approximate that as a circular path. And understand, although we can analyze the object when it's at the top of the circle, the bottom of the circle, or anywhere in between, we're going to pick just the 2 extremes, the top of the circle and at the bottom of the circle, the top of the vertical loop and the bottom of the vertical loop. Now, at the top of this vertical loop, when this car, or when I swing my keys around in a circle, right, like this, could be my keys as opposed to the car, whatever it is, going around in the vertical circle. What force or forces act on this, whatever it is, car, keys, whatever? Tell me something that acts on this object at the top of the circle. Yep. Gravity, of course it does. Gravity acts which way? Good. So we're going to draw that down. In fact, at the bottom of the circle, gravity also acts, right? Which way does gravity act when we're at the bottom of the circle? Downward, of course. And gravity is going to be just the same value. We're at the bottom of the circle. Right, so far so good? All right, good. What else acts when you're at the top of the circle, or bottom of the circle if you find that easier? You know there is something else, because in the absence of anything else, if it's just gravity, what happens to you? If you're the person going around the circle, what happens to you if there are no other forces besides gravity? You will go straight down. That does not happen when you're in a circle. Right? When I swing those keys around vertically like this, these keys do not fall straight down. Nor when you're on a roller coaster do you fall straight down when you're at the top of a vertical circle. That would be bad. So what other force acts here? What is it? It's the normal force. Good. Which way does the normal force act when you're at the top of the circle? Usually acts straight up, right? Although we have seen some situations where it doesn't act straight up. If you're on an incline like this, the normal force acts like this, right? Up at an angle. Which way does the normal force act when you're in a loop? At the top of the loop. How about at the bottom of the loop? That's a little bit easier, okay? At the bottom of the loop, which way does the normal force act? It acts straight up. And the normal force at the bottom of the loop must be bigger than gravity, because if it isn't, then you're not going to stay in the circle. Right? Think about that. You need to stay in a circle, you need a centripetal, with a P, force. That centripetal force points toward the center of the circle. If the force toward the center is smaller than the force that's acting out, or the force of gravity, then you're not going to stay in a circle. So that Fn has to be bigger than Fg. What about the top of the circle? Which way does gravity act, Christine?
It's acting down.
Good. The normal force acts down. Now, how big is the normal force? Depends. Sometimes it's smaller than gravity, sometimes it's bigger than gravity. It depends upon how fast you're moving. So we can't really draw that as to scale right now, because we don't know how big it is without some numbers there. We know that at the bottom it's always bigger than gravity. At the top, who knows? Depends how fast you're going. Now, here's the big connection. Here's the big thing that I really want you to be able to answer. Okay, more than, what Christine just answered, which way is the normal force, more than whoever answered which way is the normal force at the bottom of the circle. This is the big one. Okay, this is the big one. If I'm analyzing this problem, either one of these problems mathematically, what do I do next? I'm not going to answer that question. I'm going to stand here until somebody gives me an answer here. What do I do next? Good. Excellent, McKenna. The next thing I do is calculate the net force, right? Whenever I have a free body diagram, and that's what this is, right, is a free body diagram. Whenever I have a free body diagram with two forces acting, when they're all in the same dimension, I don't have x and y here, I just have y, right? Force of gravity down, normal force either up or down, they're all in the same plane. I'm going to say F net is equal to the sum of the forces. So let's do that right now. Let's say F net is equal to Fg plus Fn. And I'm going to do the exact same thing down here, right? F net is equal to Fg plus Fn. Now, there must be a bit of a difference between the top one and the bottom one, because direction's different. But at the end, I'm still going to set it up the same way, because it's still the same forces. Now, the next step at this point would normally be to say F net is also m times a, right? Well, F net is still m times a, but what kind of a are we dealing with here? What kind of acceleration do we have? Centripetal acceleration. So F net, this time, instead of just saying m times a, I'm going to say F net is mv squared over r. So in other words, the centripetal force, which we said last week is always caused by something, in this case, the centripetal force is caused by gravity and the normal force. So it's always caused by something. Well, it's caused, in this case, by two things. Gravity and the normal force. At this point, if you had numbers, you would sub in those numbers and solve for something, depending upon what you were looking for. But you have to be careful about signs. I want to take a look at those signs right now, and then we'll do an example. Force of gravity is, in both cases, going to act which way? Down. So in both cases, Fg will be negative. Now, don't sub in the negative sign until you plug in numbers, right? Just like before, we don't put in negatives until we put in numbers. Fn, when you're at the top of the circle, which way is Fn acting? Downwards, so it's going to be negative as well, right? What about the bottom of the circle? Fn is up, so it's going to be positive. Good. Now, this is the one that provides people with a little bit of trouble. The centripetal force, when you're at the top of the circle, which way does it act? Let's think about that. You're at the top of the circle. The centripetal force always points toward the center. Where is the center? Down from you, right? It's below you. So the centripetal force must be negative as well. But again, don't sub in a sign for that until you plug in numbers. When you're at the bottom of the circle, this is the really confusing one because you've got a force up and a force down. Which way is the centripetal force this time? You're at the bottom of the circle. Blake, when you're at the bottom of the circle, where's the center of the circle relative to you? So it's going to be good. But again, we don't worry about any signs for any of these variables until we actually sub in numbers for those variables. All right? Does this make sense? Now, one thing that I want you to understand here is that we said at the beginning of this unit that uniform circular motion is circular motion with a constant speed. There would be a slight change in speed in this, wouldn't there? Because as you go up, you'd slow down, right? We're going to assume in these questions that you're still dealing with a constant speed going around there. Okay? All right, let's take a look at this question on page 264. It says a bucket of water with a mass of 1.5 kilograms is spun in a vertical circle on a rope. The radius of the circle is 0.75 meters, and the speed of the bucket is 3 meters per second. What's the tension of the rope at position C, as shown in figure 5.31? This. All right, we've got, what are we looking for? The tension of the rope at position C? That's like the normal force, right? Okay, if we're talking about a roller coaster question, then it would be the track pushing up. If we're talking about a bucket question with a rope here, then the force of the rope would be the normal force. Right, so let's draw this free body diagram here. I'm just going to redraw this whole thing here. Let's say at the bottom of the circle, roller coaster cart, bucket of water, doesn't matter what it is here. It's at the bottom of the circle. We'll just draw it as a box there. We've got the force of gravity acting down, and we've got the normal force acting up. We know at the bottom of the circle the normal force is bigger than gravity, otherwise it wouldn't stay in a circle. At this point we'll say F net is equal to the sum of the forces. We're going to say mv squared over r is equal to the sum of the forces. By the way, what's the value of, what's the force of gravity here equal to? Not 9.81, but you're close. Okay, negative, even closer. Force of gravity is not 9.81. That's the acceleration of gravity. The force of gravity is mass times 9.81. So we'll say mass times gravity. All right? Let's sub in some numbers here. Our bucket of water is 1.5 kilograms. V is 3 meters per second. Don't forget to square that. R is 0.75 meters. Fn, that's what I'm looking for, right? The tension of the rope here. Force of gravity is 1.5 times 9.81. Now, remember what we said. Once you sub numbers in, now you got to pay attention to signs, positives and negatives. Right? What about the centripetal force here? Is the centripetal force positive or negative here? Which way does it act? I'm at the bottom of the circle. Centripetal force acts toward the center. Where is the center relative to me? Up. So the centripetal force is positive. So if I just leave it, then it's fine, right? Fn, I'm not going to worry about that because I haven't sub numbers in for Fn. Fg acts which way? Downward, so let's make it negative. Now, I don't care whether you put the negative there or in front of the 9.81, doesn't make any difference. But that term has to be negative. Now let's figure this out. Let's say 1.5 times 3 squared divided by 0.75. On the left-hand side, I get 18. Positive 18. On the right-hand side, I get negative 1.5 times 9.81. Or you could say 1.5 times negative 9.81. It doesn't matter. Tiana? Good question. Yes, it does. It needs to be in kilograms. Absolutely needs to be in kilograms. If the mass is canceled, it actually wouldn't matter But in this case, we have a mass in 2 terms, but it's not in all 3 terms. The mass needs to be in every term to cancel. Okay, that gives me 14.715, and it's negative, right? Negative because it was negative 1.5 times 9.81. Now let's take that to the other side by adding, and I get Fn is equal to 32.715, or 33 newtons. Now, does it make sense what we've done here? Like this is almost a question straight out of last unit, right? The only difference, really, the only difference between this question and an elevator question that you did last unit is that F net is mv squared over r instead of just m times a, right? Now, let's draw another connection to the last unit. Remember in the last unit we said your weight is your force of gravity. Your apparent weight is the normal force. However you feel is the normal force. What would be my actual weight here? How heavy am I really in this question? Or how heavy is this water? The mass is 1.5 kilograms. The weight would be 14.715 newtons, right? That's the actual weight, m times g, 14.715. What's the apparent weight? How heavy would this water feel in this question? 33 newtons, because normal force is apparent weight, right? So this water would feel more than twice as heavy as it really is. Okay, that's what you're going to find next Tuesday, is that you're going around that loop. Okay, you have a weight of, we're going to say, because my weight is about 700 newtons, we'll say yours is about 700 as well, although it could be more, it could be less. When you're around that loop, you're going to feel upwards of, well, between 2,000 and 3,000 newtons. You're going to feel between 3 and 4 times heavier than you really are. That's going to be the normal force. And that's one of the things that you'll have to calculate on your assignment after next Tuesday. All right? So we'll get 2 questions, please, on page 264 then. Just real quickly, why did I not ask you to do question 2? Okay, why did I not ask you to do question 2? Using the information in example 5.7, the one we just did, find the tension of the rope at position B. At position B. Where's position B? Why did I not ask you to do that one? Here's position B. Which way would gravity act at position B? Down. Which way would the normal force act? We could solve that, right? We could do that. But it wouldn't just be F net is equal to the sum of the forces. What would we have to do there? We have to do a vector analysis then, right? Because we've got 2 dimensions. Okay, we don't have to do that because we are only responsible for the extremes, the top and the bottom. You could if you had to, but we won't have to do that. So that's why I'm asking you only to do questions 1 and 3.